Section 20.2, Balancing Oxidation Reduction Equations. Very, very important section, and very hard for a lot of people because there's lots of steps and you have to learn something. I think that as we practice this, you'll be very good at this. This is not hard. This is very, very similar to simply balancing equations. In fact, balancing equations is part of what you're doing here. There's just two things here in this type of reaction that you have to keep in mind that we didn't have to keep in mind in a non-oxidation reduction equation. Normally, we have to remember that there is a law of conservation of mass. The same amount of matter is at the beginning of a chemical equation and the same amount of matter is at the end. So all of the Legos are simply broken apart into pieces and then reconfigured. No more Legos come in and no Legos go out. It's a closed number of mass, a closed mass. So the exact same amount of mass at the beginning and the same amount of mass at the end. Doesn't matter what something turns into, you're going to have the same amount of matter at the beginning and the end of a reaction. The same thing happens with electrons. If you remember, there's two major types of reactions in chemistry. You have acid-base reactions where you have protons that are changing, where protons are being donated from one to another. When you have an oxidation-reduction reaction, you are sending electrons from one thing to another. Electrons are being shared or passed around. So you have to find out where the electrons went. If you can balance where the electrons went and balance where the mass went, as long as you have mass on the same side and the charge on the same side, then you know the whole picture of what's gone on in a reaction. That's why it's just one step harder, one step more complicated. But it's not really that bad. You just have to practice it, okay? So I'll try to help you to see. Now, tables like this always make me tired because there's like, oh my goodness, there's already 7 steps. Just look at the steps and see, are they logical to you? Do you know what you would do if you were going to do a problem? Okay, so look at it. Step 1, write the unbalanced ionic net ionic equation. So you take out the spectator ions and write a net ionic equation that's exactly everything on the left and everything on the right. Then step 2, you decide which atoms are oxidized and which atoms are reduced and write 2 unbalanced half reactions. So anything that's gained electrons, okay, that's being reduced, you take only the things that are gained on both the left and right and write it by itself. Then everything that's oxidized, anything that's lost electrons, you write it by itself. So you separate the balanced equation into 2 parts, the part that's gaining electrons and the part that's losing electrons. The next step is exactly like balancing a normal equation. Okay? You balance everything except for oxygen and hydrogen. And you remember when you do balance a normal equation, you're always going to balance oxygen second to the last, and you're always going to balance hydrogens last because they're the ones that will give you the headache. So you balance all the easy stuff first, okay? Then, in order to fix the oxygens, all right, this is actually easier than balancing equations. When you fix the oxygens, if you have more oxygens, say, on the right, you're just going to add water molecules on the left. As many oxygens that you have left over on the right, extras, you're going to add waters on the left. So that's much easier than balancing. You don't have to go back and forth and back and forth. This is not hard. These balancings many times are not hard at all. There's just more steps, but the steps are easier. I would rather do a lot of easy steps than 2 or 3 very hard steps. There are many balancing equation problems that are harder than oxidation reaction, but most people think redox reactions are harder. Now, when you've added the waters, what you've done is you haven't just added oxygens, you've added hydrogens and oxygens. That means that whatever extra hydrogens that you messed up by adding on one side, you have to add protons on the other. Now, this is only in the case that you have acidic conditions. Remember that an acid is protons. Protons and water. That's what an acid is. Protons and water. So in order to balance the oxygen, if you have it at acidic conditions, you're going to add waters to balance the oxygens. And then on the other side, you're going to balance the waters with hydrogens so that everything cancels. So this is real simple, not hard. Okay. Now, step 5. You balance each half reaction for charge by adding electrons to each side with a greater positive charge. So if you have electrons gaining, so you're becoming reduced, okay, then the original side is going to have more positive charge. So you are going to balance both sides by adding electrons to the front. If something is oxidized and losing electrons, then it has more charge on the left, and you'll add electrons on the right. You're going to add electrons on the other side to balance the charge that you have. Whatever the most positive side, that's the side you're going to add the electrons to. That's step 5. Oh, I failed to mention in step 5 also, you have to have a common denominator so that you have exactly the same number of electrons on both. So if you have, say, 2 electrons on both sides of the first half and then 5 on the next, you need to multiply them both so that they will both have 10 electrons so that they will be exactly balanced. You want the same number of electrons on the left and the right. Step 6, you add the two together. You cancel anything that's on both sides, kind of like spectators. You cancel them all. Then you check your answer by seeing if all the atoms are the same on both sides and all the charges are the same. That's how you do it. So I'm going to walk you through slowly, and then I'm going to do a problem for you so that you can see it all done at once, and I'll do it with you. Here's our example. Balance the following net ionic equation in acidic solution. You have dichromate plus chloride ion yields chromium 3 cation plus chloride gas. So if I were to do an original balance the equation, I would I've got chromiums on this side, chromiums on this side, and try to finagle it to where they're the same on both sides. It's a little bit of a different setup when you are trying to balance both matter and charge. So the first thing I need to know is which ones are going up in charge and which ones are going down in charge. The ones that are going up left to right are being oxidized. The ones going down in charge left to right are being reduced. So let's start with the dichromate. The oxygen of the dichromate is -2. Its oxidation number is always -2. There's 7 here, which means that the negative component of the dichromate is -14. The whole charge is -2, the whole charge of the ion. That means what balances what plus -14 equals -2? It has to be 12. 12 minus 14 is -2. But I've got 2 chromate ions making up that 12. That means each of these chromate is +6. So originally, the chromium has an oxidation number of 6 in the dichromate anion. In the chromium 3 cation on the right, obviously it's 3. That's the oxidation number because chromium 3 plus is 3 plus. So going from 6 to 3 is going down in charge. That's reduction. So if you go down in oxidation number, that's being reduced. So the part of this balanced equation that's going from dichromate to chromium is the reduced part of this. So it's going to be written separately. It's a half reaction. You're simply going to write the dichromate on the left, an arrow, and then the chromium on the right. If that is the reduction, then the other one must be the oxidized. So I've got chlorine, that's -1. And this chlorine gas, which is in the free state, this is the normal diatomic form of chlorine, the normal elemental form of chlorine, is 0. So going from -1 to 0 must be going up in oxidation number, so therefore it's oxidized. So here we have the 2 unbalanced half reactions. We have the dichromate going to the chromium 3, and we have the chloride going to the chlorine gas. So the dichromate is +6 going to chromium +3, so it is being reduced. The chlorine or chloride ion, which is -1, going to the chlorine gas, which is 0, is being oxidized. So the first step after writing the half reactions is simply balance everything that's not oxygen and hydrogen. So if I have 2 chromiums on the left, I have to have 2 chromiums on the right. If I have 2 chlorines on the right, I have to have 2 chlorines on the left. Easy, easy. So look to the right first. Since I have oxygens here, okay, I've got 7 oxygens on the left. I have to add 7 oxygens on the right, and I'm doing it way easier than balancing equations. I'm just going to add 7 waters to balance it. So this is seriously easy. If I have 7 on the left, I come over here and add 7 waters. Problem is, by adding waters, I've also added 2 times 7. I've added 14 hydrogens. So on the other side, to balance what I've just done by messing it up, I'm adding 14 protons to get rid of the hydrogens. Okay, so let me review. My chromiums are balanced. I now look at my oxygens. I've got oxygens on the left, nothing on the right. So I'm going to add waters on the right to balance the 7 oxygens that I've got on the left. So I add 7 waters. But that's added 14 hydrogens. So on the left, to balance the hydrogens, I add 14 protons. On the bottom one, I don't have anything because there's no oxygens to play with, so I don't have to add any oxygens, and I don't have to add any hydrogens. Remember that this original one was an acidic solution. So since it's an acidic solution, I'm going to add waters and hydrogens. If it's basic solution, I'm going to add waters to get rid of to balance with the oxygens, and then add hydroxides to balance the hydrogens. So that's the only difference. If it's acidic, I'm going to add protons. If it's basic, I'm going to add hydroxides. Now, on the dichromate on the left, there were 2 chromiums, each with an oxidation number of positive 6. On the right, there's 2 chromiums, each with a oxidation number of positive 3. That means there's 12 here and 6 here. That means that there are 6 more charges, positive charges on the left than the right. So to balance these charges, I'm going to cancel out these positive charges with electrons. So whatever I have the higher charge, whatever is the highest charge on the left, in this case, I'm going to add electrons to it in order to balance it. So I've got a 12 on the left, a 6 on the right. I'm going to add 6 electrons on the left so that they will be equal. In the oxidation, I've got 2 negative 1s going to 0. That means 0 is 2 bigger than negative 2. The higher charge is actually on the right. Even though it's 0, it's higher than negative 2. How much higher? 2 electrons. So I'm going to add 2 electrons on the right to balance it off. That way the charges are exactly the same on both sides. Now ultimately we need to add these 2 half-back reactions back into the one reaction. So I need to balance the number of electrons that I have on both sides. In the reduction, I had to add 6 electrons to cancel all the charge. In the oxidation, I had to add 2 electrons on the other side in order to balance the charge. Well, I need to make them the same. I can't have 6 on one and 2 on the other. So I look and say, how many times does 2 go into 6? It's 3. And so what I'm going to do is I'm balancing it by multiplying both sides of the bottom reaction by 3 so that I'll end up with 6 electrons. Then I'll have 6 electrons added on the left on the top. I'll have 6 electrons added on the bottom on the right on the bottom. And then when I add them together, all the electrons cancel and all my electrons are accounted for. The last step is simply to add them together. You're going to add everything on the left to the left, and you're going to add everything on the right and put it on the right. What you're going to not put is the electrons, because the electrons are the same on both, so they can cancel. Also, anything that's the same on both, if you had waters on on both sides, or hydrogens on both sides, or whatever you would have that's common to both sides, you would cancel those spectators out. So you're only looking at things that are together. So when you have a dichromate going to chromium and chlorine or chloride going to chlorine gas, the balance equation is going to have some extra steps, extra components. You're going to have hydrogens, you're going to have waters, and then you're going to have coefficients just like a normal balanced equation. So it's a balanced equation, but you're balancing not just matter, but you're balancing charge.